Yeah. All right, everybody. Thanks for coming in. I know it's tough to do classes remotely, and it's certainly a new experience. And 107 is definitely not one of those classes that you want to do remotely, especially if you signed up for it face to face. But the reality of the world is the way it is at the moment, and this is the way that we're doing it. And so, without spending a lot more time sort of prefacing the reality of the situation, let's get into it. And so what I'm going to do is I'm going to start with my iPad, and I'm going to switch over. Hold on, I messed up here. Let's try that again. Dial in, close, stop video. Okay, and then I should be able to share my screen in just a second. All right. So this is my whiteboard. This is my chalkboard for the day, and I'm very much. If you got to know me in class, you would know that I'm very much a chalk talk type of person. I don't really use PowerPoint slides until they just get to the point where they're so good or so indispensable that I'd be doing you a disservice to not use them. And so I want to start off with all of the bits of chapter one. Uh, and chapter one involves essentially only one topic that is going to be examined on, and that is the scientific method. I think the important thing about the scientific method to get across to everyone is this difference between theory and hypothesis. A lot of times you hear theory used almost in a way to insult or to be derogatory. The phrase that comes to my mind is "that's just a theory," right? That's just a theory. But the word theory actually has a definition that implies that indicates the phrase "that's just a theory" isn't really really indicates that you misunderstand the definition. And so we'll get to that here in a second, but I want to go through the scientific method and let's think about how this works. And so when I say the scientific method, what I mean is the process by which scientists and those that are practicing science use to organize their knowledge. When we report something as scientific, and I'm going to use the word fact in quotations, but when we report something as scientific fact, it's gone through this process, or at least it's part of this process. But all scientific knowledge starts with one thing, and this is an important word to think about. What happened with Newton when the apple fell off the tree and it hit him in the head? Newton had an observation, and in this case, the observation is the reality of the apple colliding with his noggin and causing him to get a little lump. And if it was a particularly large apple, it was maybe it made him dizzy. This is observations really are the heart of science. When I say observation, I mean anything that we can observe through our eyes or our senses, or that we can measure with instruments. If you think about it, every single scientific experiment is designed to give us observations. If you think about it from the very simple standpoint of measuring something with a ruler, the ruler is an instrument, and that instrument is designed to give us an observation, and the observation is intended to allow us to draw conclusions about the distance or the length or the width of an object. So an observation at the end of the day is some point in that is something that gives us data. An observation leads to data, and data and observations really are the same thing. Okay, it doesn't really work very well in an online environment, but see if you can track with me for a second. And I've got chat open and I've got the participant window open. So if you have a question, feel free to type it in chat. If you want me to stop the recording and address a more complicated question, raise your hand or say something in chat and I can do that. This next part doesn't work so well in an online environment, because at this point what I would say is the observation can lead us to a hypothesis. And I'm certainly going to embarrass myself by misspelling things. So if I ever misspell something and you don't know what it is, ask me and I'll certainly I'll sort that out for you. So let's go back to Newton and this idea that Newton's has this observation with the apple, and that Newton's ultimately going to start to describe the theory, the gravitational theory. And one of the things we might say is we might develop a hypothesis, and the hypothesis is an initial explanation. I think that if you even were halfway paying attention in 8th grade science, you couldn't have made it through high school without sort of understanding that a hypothesis is really like the common phrase is educated guess or an initial explanation of something. So let me write that just right below it. Initial explanation. Also, let me know in chat if you have any problems seeing anything. I think it should be filling most of y'all's screens. It seems like it should be okay. But if you're using an iPhone or a smartphone, it might start to get a little difficult to see. So one of the initial explanations or educated guesses or predictions about the future that Newton could have made was he could have said the following, right? And this is the part that doesn't work so well. He could have said, apples are attracted to heads. I think at this point you might agree with me. I don't know if you disagree or not, and it's hard to, because usually I would see your faces and get reactions, but certainly that's consistent with the observation, right? He's sitting under a tree, apple falls, hits his head. One possible initial explanation, one possible hypothesis that is consistent with the observations is that apples are attracted to heads. And so in class, I would make the same sort of analogy with erasers, and I would hold an eraser over someone's head. And I know it's not so funny online, but I'm going to go with what I got. And we'd giggle about it, and they'd dodge out of the way, and we would realize really quick that if I held an eraser or an apple over someone's head, it would proceed directly towards their noggin. And this is the point where I would stop and say, what did I just do? What did I just do by coming up with this hypothesis and then holding the apple over the head and letting it go and saying, oh, well, I thought that apples are attracted to heads. What is this thing that I just did then when I took that apple and I held it over a head and I dropped it? What was that? Just give you a second and somebody type in chat for it while I take a few sips of this delicious, delicious coffee. In the realm of scientific method, I came up with a hypothesis and then I did something. Yeah, exactly, Ria. This is an experiment. one of the things that's sort of important about words is really what are their roots. If you look at the word experiment, you come up with this idea that the root of the word experiment is to experience. And that's really what it's all about. Experiments provide experiences. Which one of the words on the whiteboard is most closely related with this idea of developing different experiences? In other words, I'm asking the question, what is an experiment really designed to do? Yeah, an experiment is designed to provide observations. So Diana suggests that an experiment is designed to prove a hypothesis. And I want to take a step back from that statement. And I appreciate her participation in the discussion. It's not quite where it's at though, right? Because in the scientific method, a really good scientist is just as happy to have a hypothesis disproved as they are to have it proved. So at its heart, an experiment is really designed to provide observations. And then what we do as scientists is we say, okay, we had this initial explanation. It was our educated guess to explain some previous observation. We did an experiment. That experiment provided additional observations. And now what we want to do is we want to say, does it support or does it not support our hypothesis? And either outcome is okay. So I hope that you see the nuanced difference in that it's not strictly to prove a hypothesis, but if you want to add words to your definition to make it as correct as possible, you would say to prove or disprove a hypothesis. But at its heart, it really is designed to provide observations. And what we do is we examine the observations to see if they support or don't support this hypothesis. So let's go back to this experiment we just did. We took the apple, we took the eraser, we held it over our head, we dropped it, we let go of it, and we all know what happened is it smashed into our brains. Does that support or does it not support the hypothesis that apples or objects or erasers are attracted to heads? One of the things I like to say in classes, certainly in their face-to-face version, is that I'm totally okay with uncomfortable silence. I assume I have yet to receive some sort of letter from the Office of Disability Support Services that indicates that somebody amongst you doesn't have a hand that they could use to type. So far, Angela and Diana and Rita have definitely, and Ria have participated in this conversation. Now, Majan says it did support that hypothesis. So we did the experiment. It gave us an additional observation. It supported our hypothesis that apples are attracted to heads. Are we done? Can we go now and proclaim it to the top of the mountain that apples are attracted to heads? No, we can't. The observation has supported our hypothesis, but so we're starting to move through this scientific method, but maybe now we have to continue to test our hypothesis. Yeah, we know. I'm acting like we don't know, but we know it's gravity, right? We know that it's gravity, and it's not the head that the apple is attached to, right? And I'm trying to pretend like maybe we don't know, right? Maybe we're back in the 1500s, and we think that the universe is run by, magical spells, and maybe it's just magic that causes things to do what they do. when we think of it that way, what other experiment might we do to support our hypothesis that objects are attracted to heads? Before, I held it over my head and I dropped it, and that supported the hypothesis that objects are attracted to heads. If it's actually true that things are attracted to heads, does it matter which direction I hold it from? If I hold the brick over this guy's head, it's definitely going to go that way, right? It's going to hit his head. If I have this guy and I hold the brick over here, if it's attracted to its head, it's going to move that direction. Which direction does it actually move, though? We know, because we know what is up with gravity, right? It's actually going to move down. And so when we do another experiment, and we find that the object actually moves down, we did a different experiment. It provided us with a different observation. And now what are we forced to do? We're forced to change our hypothesis. The observation that we got does not support the hypothesis that we initially made, that objects are attracted to our heads. And so when we go through this process of the scientific method, what I'm trying to illustrate with what's going on the whiteboard is that it's cyclic, right? It's not just a linear process. Yeah, exactly. We continue this cycle. That's right. This is what science is all about. It's about observing something, trying to explain it, and then coming up with ways to test that explanation. And those tests for that explanation leads to additional observations. The observation either supports or doesn't support the initial explanation that we made, and we change that initial explanation. So the idea that this is rigid and square, maybe I shouldn't draw it that way. Maybe I should draw it with squiggly lines to indicate that it's malleable, that it can change, and that's okay. That's certainly okay. That's part of the scientific process. And so we go through this iterative process of observing, continually observing. And if we confirm it enough, a couple of things can happen. Okay? A couple of things can happen. One thing that can happen is that if we have enough data, enough observations, we can come up with a law. And a law is something. So in this idea, we would say, okay, objects are attracted to each other based on their mass. And any object would be more attracted to the object with the most mass. And we all would say, maybe now we're more sophisticated. Maybe this cycle took us 100 years to get through. But we go, oh, at the end of the day, we're like, it's not magic. It's just that the Earth is very massive. And so everything is attracted to the most massive object. And the Earth is what's the most massive object. So we would say everything is attracted to the Earth through a force. Well, maybe we would say even it's gravity or whatever. But at the end of the day, we would say, if I continue to drop objects, it doesn't matter where I hold them, they will always be attracted to the most massive object. So in this case, it's a law, right? And so a law is something that makes future predictions. And so what I'm going to eventually get to is a law and a theory. And there is a subtle difference between laws and theories. The main thrust of the difference is that laws predict, but they do not explain. So a law of gravitation would be objects are attracted to each other. Every time I drop an object, it's going to be attracted to the most massive. And since the most massive object that we're involved with is the Earth, it's always going to be attracted to the Earth. There's no explanation in that, right? There's no explanation in why that happens. Theories are the explanation. Theories explain. They can predict future events, but the bottom line behind a theory is that it provides an explanation. But at the end of the day, going back to this idea that we had before, well, that's just a theory. Well, remember, what do we need in order for it to be a theory? We needed it to go through this process, this iterative cycle of experimentation and observation. And when we develop a theory, it's an explanation that is consistent with all of our previous observations. So to say that it's just a theory, when you say it's just a theory, what most people are really saying when they're being derogatory like that is they're saying it's really just a hypothesis. You don't really have any evidence to back up your explanation. When scientists have a theory, there's evidence to back it up. So that's the big difference. And so what are the take-home messages about the scientific method? It's a cycle. It's based on observations. And observations are what experiments are designed to do. At the end of the day, they can produce laws and theories. And the law predicts, but it doesn't explain. Theories explain. So what I want to do is I want to pause right there, because that's really the end of it. What happens though? I mean, what happens if we've developed a theory? Does that mean that we will never have an observation that goes against the theory? Is that what that means? Yeah, definitely not. Definitely not. It just means that based on all the observations that we have right now, this is the best we have. And so I also want to put in this bit, scientists we love our theories, but at the same time, we understand that while they're the most concrete thing of the scientific method, that doesn't mean that there's not the possibility that future observations will come along and say, whoa, something's wrong with our theory. And so we need to go back to the cycle. We need to go back to do some more experiments to try to tease that out and see where we're wrong and actually come up with something better. And so when we think about what's happening in science, is that I imagine it as this colony of billions of ants, and each little individual ant is doing a job, and that job goes to support this cycle. And when we talk about science, especially well understood science, you've got not only time, years and years and years, exactly, a theory can cause another cycle of testing. It really, there's this cycle of testing and observation is usually happening all the time. I mean, how long has the theory of evolution been around? Theory of evolution's been around for over 100 years, and we're still cycling and testing that, right? I mean, that's one of the major theories that people get upset about, the idea that, that there was this billions of years long evolution of life on the planet, and we've got a lot of observations that support that. and we've done a lot of experiments, and we've got now a well-tested explanation, a theory. But that doesn't mean that we're scientists and we're right. That just means that we're continually looking for other observations. But up to this point, all the observations we have support this theory. If you find one that doesn't support this theory, we'll get excited. You know, if somebody has an experiment or comes up with an observation that proves that humans were seeded on the planet by aliens, that's going to be a big deal, and they're going to be well respected in the scientific community. They're not going to be derided. Now, the key is it would have to be good observations. In other words, there'd have to be good data that supports that. Can't just be aluminum tinfoil hats. Even though we all know that aliens did seed the planet. The comment is made, evolution is continuously done by scientists and the public as well. And I would agree with that, right? We're always evolving in one way or another. Sometimes we wish we'd evolve a little faster. All right, so does anybody, I want to stop right there and see if anybody has any questions. Here's a statement. Let's do a little bit of testing before we move off. I'm going to make sure everybody's got this. Get ready to type in chat. So get ready. I'm going to take another sip of this delicious coffee while you guys poise your hands over your keyboard. The volume of a gas is inversely proportional to its pressure. Does this better fit the definition of a theory, or does this better fit the definition of a law? Okay, so we're starting to get a lot of responses, and this is a good opportunity. The majority of you say that it's a law. Maddie, you're saying your PowerPoint slides are much better and easy to read chapters than textbooks. Can I only read the PowerPoint slides? So the question is, I think what Maddie's asking me is, can I look at the PowerPoints rather than looking at the textbook? You can do whatever you want. At the end of the day, I'm not sad about what your choices are. I think that if you really wanted to make sure that you got an A in this course, you'd read the textbook, you'd skim over the PowerPoints, you'd do some practice problems, and you'd watch these lectures. If you're saying, well, if I'm only going to do one of those things, what should I do? Well, you should watch the lecture. If I'm only going to do two of those things, watch the lecture and do some practice problems. So I know that doesn't really answer your question, but at the end of the day, if the PowerPoints work better for you than reading the textbook, do it. It's fine. Now, I'm getting a lot of answers, and most of the answers say law. Some of you guys are coming up with theory. And so let's go back to the definition. Remember that laws make predictions, but do not explain. Remember, an explanation answers the question why. A theory explains. It does answer the question why. So let's get back to this idea of the statement. The volume of a gas is inversely proportional to its pressure. Does that answer the question why? Yeah. And I'm even starting to see some of you who said theory say, no, that really doesn't answer the question why. No, it doesn't. It really does sort of make a prediction, although the prediction isn't, isn't spelled out, doesn't say if this, then that. It says the volume of a gas is inversely proportional to its pressure. So what it's implying is that if you increase the pressure, the volume should go down. So it is implying there's a prediction there, right? If you decrease the pressure, the volume should go up. That's the implication of the prediction. And so let's try a different one before we move on here. Let's try this one. Pressure in a gas is caused by small particles in motion colliding with the walls of the container. Yeah, in this case, it really is explaining it, and it's answering the question why. Why is pressure, or what is causing pressure? How is pressure in a gas developed? Well, it's done by small particles in motion colliding with the walls of the container. Maybe you can tease out a prediction as well, but that's not the point behind this. The point behind this is really answering the questions why or how. And so, you guys are all, I don't see one single person putting in the word law. Everybody's got the word theory written down, and that's exactly what I consider to be the right answer as well. This is, the blue text is an example of a theory. The brown text is an example of a law. And so at the end of the day, I think we got this down. Remember, theories explain and they answer the questions why or how. Laws simply predict future events. So what I'm going to do is I just want to pause a beat and see if anybody's got any questions. Type it in the chat or raise your hand. Okay. Sweet. Good news. And so that's really all that there is with chapter 1. And I think you guys have that down pretty well. And so what I want to do now is I want to move into the material for chapter 2. And chapter 2 is the first time we start to use numbers. And I get it. Some students this is the point where we start to get a little bit scared. And so what we want to do is we want to start with scientific notation. And then we're going to move on to units of measurement. And then I'm going to go back and talk about significant figures. So I want to do, the first thing I want to do is scientific notation. Then I want to talk about the units of measurement. Then I want to talk about sig figs. And sig figs certainly are the hardest thing to kind of in the moment that we're going to be talking about. All right, so let's get into scientific notation. What's that all? What's this all about? All right, the first thing that I want to do is I want to make sure that everyone knows how to write a number in scientific notation. I'm going to do it very generically. You know, X is actually not a good letter to use there. Let's use A. Here is a number in scientific notation. And here's the thing that students often forget, that A point A, whatever this number is, it must be greater than 1, or it can be greater than or equal to and it must be less than 10. So it's not that 25.6 times 10 to the third. It's not that that's not a real number. It's just not correctly expressed in scientific notation. In order to correctly express this number in scientific notation, it has to be 2.56 times 10 to the fourth. And so both of these numbers are the same number. If you put them into the calculator and use them in a calculation, you get the same answers, but only one of them is expressed in proper scientific notation. Is there any questions about that? This is one of the most often confused bits. This number must be equal to or greater than 1, and it has to be less than 10. Notice it's not less than or equal to 10. The largest it can be is 9.999999999. Can't be 10. Questions? Okay. All right, so what's the purpose of scientific notation? It's just to make writing numbers easier. I mean, that's all there is to it. Let me write a number down. Let me write 2 numbers down. Oh, that's tough. The question was asked, will we be able to replay this video? Yeah, absolutely. I'm recording it. And I'm gonna, when we're done and my system processes it, I'm gonna immediately post it on YouTube. I'm gonna put that link in the course, and you guys will be able to see it. That's one of the main benefits that I'm trying to develop for you guys about being in this remote environment, is that in lecture, you just have to come, and if you write the notes and if you can get notes from somebody, that's the best you can do. The one benefit about being in this remote environment is I've got a record button, and I can post this and you guys can see it. And if you get confused, you can look through the list of videos and you can say, what video was that he talked about scientific notation? Let me go watch that. Let me zoom through it and get to the point where he's talking about it. Yeah, so scientific notation really does help in making writing big, or what, but not just big numbers, Maddie. What other kind of numbers could they be? Yeah. Really small numbers. So they really help conveying the information about about the values of large and small numbers without having to do a lot of writing. And so to put the first one in scientific notation, it's like that. To put the second one in scientific notation, let me redo that. I want to make sure it's clear. What do you notice about the difference between this and that? What's the big difference? Right. Right. Exactly. One of them is negative, the other one is positive. The negative values represent small numbers. Positive values represent large numbers. And so this makes an implication, right? And so what you want to be able to do is you want to be able to convert big numbers to scientific notation and convert small numbers to scientific notation. But you also want to be able to understand what those numbers mean. So in order to test that, we're going to have you take these numbers and convert scientific numbers into their regular notation. And so you need to be able to go both ways. And so let's practice with this just a little bit, and let's see how I did this. Well, let's think about how I moved the decimal place. This is really this is the sort of the demarcation. Which direction did I move the decimal place? And I'm going to use left or right. For the large number, in order to go from large to small, from a actual note, let me rephrase that. To go from regular notation to scientific notation, I'm moving the decimal place to the left. That's where it ended up. How many spaces did I move it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I moved it 18 spaces. That's where that number comes from, exactly. So that's the order of magnitude, 10 to the 18th. It really, that's all you'll ever do. When I wrote this just a little while ago, I literally just counted the spaces that I moved the decimal place in order to come up with 10 to the 18. The same thing is true with the small number. How many spaces did I move it? Instead of moving it to the left, though, now I'm moving it to the right. Oh, that's where the decimal place ended up last time. So that was 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why it's 10 to the negative 9. So let's take a couple of numbers. Let's do the same thing with these numbers, and let's convert them into regular. Let's go the other way around, and I'll use the same numbers so we can see that we want to come up with the answers that we've already got written on the screen. So let's try that. So let's start off with A. That's what happened. Yep. Let's start off with A, and then let's do B. And so here's A. So I start with 7.462. And I want to move, so if you move it to the right, it'll be negative. If you move it to, yes. So there's two ways that you need to think about it, and you need to think about them both ways at the same time. Negative exponents mean small numbers. When I convert a small number into scientific notation, I have moved the decimal place to the right. But be careful. When I go the other direction, I'm moving it to the left, and you'll see that in a second. So I do want to sort of unhook it from this idea strictly of left and right, because remember, it's actually both ways, depending on if you're converting it to scientific notation or converting it from scientific notation. And so don't just hang your hat on left and right. Think about whether the number is big or small. But in this case, if you move a decimal place from a number in regular notation to the right, the exponent will be negative. And so that's how I'm going to answer that question at the moment. So let's take a look at this one. Let's 7.462, and then the order of magnitude tells me that I should move it 18 spaces. So 1, 2, let's change colors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's the decimal place. So what do I fill in all these little spaces? These are where zeros go. So the first thing then I want to do is I want to erase this decimal place because I don't actually know what goes there yet. But I do know that I need to fill in some zeros. 0, 0, 0, 0, 0, 0, 0. There's a decimal place. Now, if I want, I can come back and put in some commas. Now I've gone the other direction. Anybody have any questions about that? Okay. Now let's do B. With B, I start off with 3. I'm going to put it right here. And then I move it 9 spaces. The question is it not always going to be a 0? The numbers that you fill in these spaces will always be zeros. Once all of this, and we're going to talk about this in a second, but all of the non-zero numbers are always expressed in scientific notation. When I move the decimal places, once I've moved beyond the non-zero numbers, the rest are zeros. Does that answer your question? Yep. Okay. So let's start off with this one. Now it's 10 to the negative 9. Here's where the decimal place is. And so I want to move that decimal place 9 spaces, but I'm going to move it in the opposite direction. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the new decimal place. The 10 to the negative 9 tells me that I have a small number, so I need to move the decimal place in the direction that makes it a small number. The 10 to the 18th means that I have a large number, so I moved the decimal point in the direction that turned 7.462 into a large number. I'm now, in this case, in B, I'm moving the decimal in the direction that turns 3 into a really small number. One, two, three, 4, 5, 6, 7. Oh, that's 8. 1, 2, 3, 4, 5, 6, 9. 8 zeros, 9 spaces. And so I'll erase this decimal point because I don't need it anymore. And now I've gone the other direction. Does anybody have any questions about this before we just try to do some practice real quick? Okay, so I'm gonna type in chat, and I'm gonna show you how we can use chat. There isn't actual scientific notation, but we could do this. We could do 3.4 times 10, and then I can do this. So I can do 10 caret 3, and the caret, the little upwards triangle or the little upwards chevron, indicates this next number is an exponent. The same way I can do 7.89 times 10 caret negative 5. So both of those, that's one way I can answer some questions in chat and express them correctly. So let's do one. Let's do a practice real quick. Actually, I want to keep these here where they are. So 2,500,000 60. Let's express that one in scientific notation. So if you got a pen out, do it on the piece of paper, but then once you got it on a piece of paper, let's put it up in chat. So just give you a couple of seconds to do that. So that's 2,560,000. Make sure that it's clearer. Starting to see some answers come in. Yep. Right. So let's take a look. Now the decimal point is not necessarily listed, right? I'm not necessarily going to show you the decimal place in the number, but it's implied, right? It's implied that it's right there. And so this number is bigger than 1. Since the number is bigger than 1, we know that the exponent is going to be positive. And so where's the space that makes the number between 1 and 10? Well, it's right here. Here's that location. So let's move the decimal place that way. 1, 2, 3, 4, 5, 6. And so now I've finished. It's 2.56 times 10 to the 6th. Yeah, good job, everybody. Good job. All right, let's do the same thing. Let's do that again, but let's try a small number this time. See, let's do this one. $0.000404. The little numbers are a little bit harder to deal with, I think. It's a little bit more confusing. Let's count the decimal places and let's figure out where I would be in order to make the number between 1 and 10. So if I put a decimal point right there, I'll get 4.04, and that's what I want. Yeah, that's what I want. And so, yeah, I see you corrected yourself. That's great. That's great. So I see that too, but let's count the number of spaces. If this is the spot that I want to put the decimal place, how many spaces over must I move it to get it there? Is it 6 spaces? 1, 2, 3, 4. So it's 4.04 times 10 to the negative 4. How is that? You want another one of those small number practice problems? Yeah, let's do another one of those. Let's do another one of those. All right, let's do 0.000007602. Here's the spot that I want to use to make it a number between 1 and 10. That's the number that I'm looking for. 7.602. And then how many spaces did I move it to get there? 1, 2, 3, 4, 5, 6 spaces. So it's times 10 to the negative 6th. Okay, let's practice going the other direction then. Let's take some scientific notation and let's convert it into regular notation. So let's do 2.5 times 10 to the 5th. Write that number out. So the question is asked, how do I know which spot? And so remember that the number, whatever this value ends up being, it has to be between 1 and 10. It can be equal to 1, but it has to be less than 10. So in this case, if I put the decimal point here, then I get 70.6. That's not between 1 and 10. If I put the decimal point here, then I get 706. That's not between 1 and 10. So in order to get it, if I put the decimal point here, I get 0.706. That's not between 1 and 10. So if I put the decimal point there, I get 7.06. That's between 1 and 10. That's how I know which spot. Does that answer your question? Cool. Excellent. Excellent. And so I see folks starting to answer this one. Some folks have used commas. Some folks have not used commas. It doesn't really matter. Commas are an optional thing. And so let's take a look. We're going to start with 2.5. And I'm going to move the decimal place. And I'm going to make since this is positive, I'm going to make the number bigger. So I want to move the decimal this way. 1, 2, 3, 4, 5. Fill it in with zeros. Then go back and erase my decimal. And then what do I have left? I have 2, 5, 0, 0, 0, 0. So 250,000 exactly. All right, any questions about that? I think folks, based on the limited amount of responses that I'm getting, maybe getting about 15% participation in the chat window. Seems like those folks are getting it down. So what I have to do, I just have to do this. I have to assume that if you're not participating in chat, it's because you're bored to tears and you wish I would move on. That's the assumption that I'm making. And so that's what I'm going to do right now. So let's try a small number. Let's try 4.702 times 10 to the negative 7. Let's try that one. Convert it the other direction. Give you a couple of seconds to respond to that one. Yeah, that looks right, Norm. So let's take that 4.702. Let's move the decimal place. We're going to, since it's 10 to the negative 7, we need to make it smaller. And so I want to make the number smaller by moving the decimal place this direction. 7 spots. 1, 2, 3, 4, 5, 6, 7. So here's the new decimal spot. So I can go ahead and erase this one. And now I can fill in zeros. And so rewriting, I get 0.0004702. And I can throw a 0 here just to hold place if I want. It's okay if you don't, though. And so This is definitely something I'm going to test you on. It's definitely going to be on quizzes and exams. And then later on, after I test you, I'm just going to assume you know how to do it. So let's pause a beat before we move on from scientific notation and talk about the different units of measurement. And let's make sure that everybody's got what they want to get as far as questions answered. Does anybody have any questions? Okay. All right, so I want to talk about the units of measurement. I just want to talk about, I'm skipping, let's see. 26. We're gonna get to significant figures. Be careful with the difference between O and 0 in your chat window. It's okay. We'll get to sig figs here in a second. What do I mean by basic units of measurement? How do you guys, what's the unit of measurement for distance when you're driving down the road? Type that in chat real quick. Yeah, right, exactly. Everybody knows it's miles. That's the unit of distance when you're traveling down the road. And that's what I mean. This is what I mean by the units of measurement. But specifically, I want to talk about the SI units. I'm not French. I don't speak French. I've taken a little bit of French. SI means System International or something. Maddie's saying kilometers if you're not in the United States. Any other country except the United States and Britain and Australia use meters. I think even Britain uses meters. Maybe it's just us in Australia. So, but what else could we use? What other units do India? Do they use miles in India? I thought India used kilometers. Yeah, I was thinking that. What other units of distance do we know? We talked about miles, we talked about kilometers, meters, sure. Feet, exactly. Yards, football fans. Inches, exactly. Centimeters, sure. So these are all different millimeters, right? Exactly. Really small things. I've got a device right here. If you can see in my camera window, this device is designed to measure very small measurements very accurately. So that one's in. Ooh, Sandra comes up with one of my favorites, light years. Exactly. Light years is an interesting unit of distance because the word light years has a word that means time. But this is actually a distance, and the distance is the following. It's how far light travels in a vacuum over the course of a year. And so remember that even though when we flip the light switch, it seems instantaneous to us, it does take some measurable amount of time for the light to get from the light bulb to our eyes. If you let that light travel in space for a year and then measure that distance, that's a light year. That's a great one. That's my favorite. I'm a space nerd if there ever was one. Okay, and so we've come up with all of these different units of measurement, but the SI units are the specific units that are used in the scientific I can't say the French word. I'm just going to say these are the units that are SI based. And so when we could use feet, we could use kilometers, we could use meters, we could use whatever. These are the units that are the base units in the SI system. And so for length or distance, The SI unit is the meter. The symbol is M, little m. In time, the SI unit is the second. What could it have been? Right, it is seconds. What could it, I mean, what are other units of time? Minutes, hours, days, months, years. Exactly. Those are some other units of times. The wheel, oh, the week. Yeah, the week is a unit. Yeah. I thought you were coming up with some ancient time frame. You know, the word foot comes from the idea that the standard unit of measurement was whatever the distance of the king's foot was. And so what a foot, you know, and if you still go to construction sites today, you know, a person's foot is around 12 inches. If they're, you know, depends on where, you know, maybe the average construction worker. And so, you know, they'll definitely just sit there and use their feet to kind of measure off a rough distance in feet and foot or in feet. Temperature. What's the SI unit for temperature? Now, Fahrenheit is definitely the non-SI unit. And I know all of you guys are thinking it's Celsius too, but it looks like Nor and Diana are actually the ones that got this one down. It's not it's not Celsius and it's not Fahrenheit, it's Kelvin. And that's K. And this is the reason why we use Kelvin. Kelvin is called the absolute temperature scale. And the lowest temperature on this scale is equal to 0. In Celsius, that's the conversion factor. That's right. Celsius plus 273 equals the temperature in Kelvin. The reason why we use the Kelvin scale is because there are no negative temperatures. In both the Fahrenheit and the Celsius scale, there are negative temperatures. And so and this is just because we arbitrarily connected them to water freezing. And once we arbitrarily connected them to water freezing, it turns out then we can have temperatures colder than 0. So we've come up with a scale that has no negative temperatures. This works better in our math, and that's the Kelvin scale. What about mass? Mass is the next one. Yeah, it is the kilogram. It's not the gram. It's the only one that has an actual prefix. And so notice that meter doesn't have a prefix. It's not kilometer or centimeter. Seconds doesn't have a prefix. We're going to talk about that more in a second. Kelvin doesn't have a prefix. We're going to talk about that more in a second. Kilogram is the only SI unit that has a prefix. What's the unit for quantity? Liter is a volume. It's not a quantity. Quantity is the number of things. What are some words that you know that mean a particular number of things? Exactly, Rhea. Dozen. Exactly, Gabby. Dozen. That's a number that means, dozen is a word that means 12. There's another word. What does pair mean? That's a word that means a number of things. 2. Yeah. How about gross? Gallons are, again, that's a gallon is a measurement of volume. And a volume is a derived, no, actually it isn't a derived unit. Let's talk about volume in a second here. Volume. Does anybody know what value gross is? Yeah, it's 144. The quantity in the SI unit is called the mole. Its symbol is MOL. And because you now know scientific notation, I'll write it down. The number of things that is a mole is a really, what, big or small number of things? Yeah. It's a very large number. 6.022 times 10 to the 23rd. There's a lot of zeros after that. Yeah, quad big for sure. We're gonna have some practice converting this number because we're gonna get into moles a lot more, and moles is one of those things that really does present a lot of confusion for lots of students. And so we'll come back to this a little bit later here in chapter 3, but I'm gonna write it down for you now. Volume is the liter. Symbol is L. It can also be little l. I'm just gonna write it down as big L. I'm going to actually draw the line right here. Here are the base units that are in between the two lines. I'm leaving liter out because liter is actually, volume is actually a derived unit. And I'm going to talk more about that here in just a second. Maddie, 144, the word for that is gross. It's not really used in common language. It's typically used in manufacturing. So when you're creating lots of a particular product, then you order them in different quantities, and a common quantity of ordering products is in a gross. And the word gross comes from, there's another word that we haven't talked about, and it's the word case. Yeah, it's 12 dozen exactly. And so it's 12 times 12, and so that's 144. And so it would be 12 cases. And a case is the most common definition of a case is 12. So yeah, it's really not used in conversation much anymore, and it's really only limited to manufacturing at this point. It's just like we don't say fortnight anymore, right? Does anybody know what that fortnight is? A unit of time. Does anybody know what that one means? It's not a first person shooter. No, that's not what it is. Right. No, it's not 120 days. It's 14 days, 2 weeks. So that's a fortnight. And so that's another example of something we just don't use anymore. All right, so let's talk about derived units for a second. So we've got into scientific notation. We're well in the units of measurement. And the next thing we're going to talk about is sig figs. So we'll leave that to the bottom here. But let's talk about a derived unit. This is something that is a measurement using a combination of base units. And in this particular discussion, what I mean by base unit is one of those those 5 base units: length, mass, time, temperature, or quantity. And so a derived unit is a measurement using some combination. And when I mean combination, I mean a mathematical combination, mathematical. And so I think volume is the first one to start with. So let's talk about this. Actually, let's start off with area. Area is a unit of measurement. The area expresses how much space in 2 dimensions is taken up by this square. How do I calculate an area? What's the definition of an area? You guys got that one? Got about half an hour left. Yeah. Side times side, or length times width, whatever the case may be. Length times width. And so what's the base unit for lengths? The base unit for length is the meter. So what do you get? What unit is area if you take meters and you multiply it by meters? You get meters squared, right? And so this is something that I want everyone to sort of kind of to grasp at this point. And this is definitely a challenge for a lot of students. It's this idea that you can take a unit of measurement like meters or seconds or whatever, and you can do math with them. The fact of the matter is, and you just kind of have to take it that you can do that, is that the unit of measurement can be used in mathematical combinations. And the mathematical combination works exactly the way numbers do, except we don't change them into new units every time. Usually we just express them as powers. So if I take meters and multiply them by meters, then I have meters squared, because anything squared is that thing multiplied by itself. So this is how I would derive the unit of area. It's a derived unit. But let's take that a step further. Instead of having a square, let's have a cube. How do I figure out the volume? How do I figure out what's the amount of 3-dimensional space? Area is 2-dimensional. How do I figure out you got it. People are starting to get it. Exactly. You're jumping, you're doing exactly what I'm hoping that you're doing. You're jumping to the answer. In order to figure out the 3-dimensional space, it's length times width. Let's do times height. So the volume is equal to length times width times height. And using the SI unit, it's meter times meter times meter, which would be ultimately meters cubed. Now, we could have been measuring in centimeters, in which case we would get centimeters cubed. And so here's the first relationship, and this is where we're going to get back to liters, that you should be familiar with. And by familiar, I do mean memorized. So this is a relationship you should memorize. 1 centimeter cubed is equal to 1 milliliter. So that's what we'll get to. Doing great. I love the participation in chat. All right, so this is something that you should write down in your notes and commit it to memory. We'll be using it a bit later on. And so this is an example of a derived unit. There's one more example of a derived unit that I want to show you. And that's the density. What's the density? The density is the mass divided by the volume. And so if I were to use SI units, it's grams, that's kilograms is the SI unit, and then there isn't an SI, we can do liter is the SI, yeah, kilograms per liter, but another one would be grams per milliliter. And so it's how much mass is taken up by a particular volume. And so we'll work more with density in a second. Actually, we'll start with that on Thursday or on Tuesday. On Monday, and then we'll do some other stuff. We'll do some more practice later on with this. But what I want to do is I want to get to significant figures. And I've got just about 20 minutes. Oh, good point. I'm reminded there is no class on Monday. That is correct. There is no class on Monday. No, the college is closed. That means no class. So we won't meet again for another week. So let's kind of go through this then. Let's take a look. Let's get into sig figs now. Before I do that, does anybody have any questions about units of measurement? All right. Sig figs we will have class on Thursday. That is correct. Sig figs are a challenge for students because they are purely theoretical. Students get confused with what they mean. Yes, and I'm sorry, Maddie, I do, and Mukti, I do mean Wednesday. I don't mean Thursday. And so I easily get confused and mix my days up. But we do have class on Wednesday, not Thursday. All right, and so let's start off this conversation. And I don't think we'll get through the whole thing. We'll start off with sig figs before we get further. Sig figs involve sig figs means significant figures. And significant figures, they tell a reader about how precise a measurement is. Remember, what can we measure? We can measure distance, we can measure time, we can measure quantity, we can measure, I'm already spaced out, temperature, there we go. So significant figures tells us how precise a particular measurement is. Unfortunately, before I actually get into the meat and potatoes of significant figures, I have to define the difference between accuracy and precision. If I embarrass myself by already misspelling that, is there 2 C's in accuracy or just 1? Good. Did I spell precision correctly? I can do the math, but I can't do the spelling. Somebody grew up on spell check. Yeah. All right, what's the difference between accuracy and precision? Is there a difference? Oh, yes. Let's use a bullseye. Yeah. Nor says accuracy is the exact number, precision is if it's close to it. Accuracy is an accurate reading while precision is near to an accurate reading. You're getting close. The language is just a little convoluted, and so I want to sort of get out to a better definition than that. Precision relates to how close consecutive measurements are to each other. If I'm using the example of a bullseye, it's how close together each of the shots are. And if we're actually using the language of target practicing, this would be the grouping of the shots. If the grouping of the shots is very close together, then this is precise. Now, in a bullseye, the position in a bullseye that is considered accurate is the middle, right? So the question is, accuracy is number and precision is exact measurements. No, not exact, because not quite, because exact actually means something, and I want to stay away from that word. So let me flesh out this definition, and let's see if you still have any questions. So precision is about the grouping, is about how close repeated measurements are to each other. Accuracy is about whether or not the measurement has attained the true value. Now, certainly one way to attain the true value would be to hit the bullseye, but I want to explain it this way. Let's take a look at this. What I'm hoping that you're seeing with the target on the left is that the grouping is not that great. Each measurement, each hit is not really next to the other one. So the precision, in other words, how big that circle is not so great. But what is the average position if I were to average all the positions out? The average position really is the bullseye. And so here's the average position is the bullseye. So this is an example of, it's in a weird way, this is something that would be accurate but not precise. We can take this same example and we can draw a bullseye that is both accurate and precise. So the bullseye in the center, where all three shots are all grouped together and they're all grouped together on the bullseye, that has the qualities of being both accurate and precise. The one on the right is just precise. The one on the left is just accurate. The precision is visualized with the green circle. How big is that green circle? The bigger the green circle, the less precise it is because of the uncertainty and where the next shot could land. Let's take a look at each of these three circles. In this bullseye on the right, if I were to predict where the next shot would occur, it's not far-fetched for me to believe that the next shot would occur inside that circle because all of the rest of them have been there. So that means there's very limited numbers of places for the next shot to appear. Somewhere in here. Same thing for this one. But for the one on the left, that circle, that visualization of the precision is much bigger. So really these shots could be, look, these could be all over the place. And that phrase that I just said, all over the place, is really what we mean about precise. And so to go back to the idea of significant figures speaks to the, no. And so Adi says, precision is more accurate, ? No, they really are two different concepts. Accuracy is really about the true value. Accurate is about what's right. Precision is about how often you are right. So let's think of it this way. If you're taking a device and you're measuring the mass, let's say that you have a cube and you know that the cube weighs 1 kilograms. And let's say that you do some measurements and you get 1.01 kilograms, 1.03 kilograms, 1.04 kilograms, and 0.99 kilograms. These represent measurements that are both accurate and precise. Why are they accurate? Well, because every one of them is very close to the true value, 1 kilogram. But why are they precise? They're precise because they're all very close to each other. Let me give you an example of some measurements that are only accurate. 1.50 kilograms, 0.50 kilograms, 1.25 kilograms, 0.75 kilograms. If you take these four measurements, add them up and divide them by 4 to get an average, the average is 1. So if you were to average these to get an answer, the answer that you get is 1. It's accurate. But are they precise? And the answer to that is no. They're not precise because the measurements themselves are not close to each other. Let's take a look at a series of measurements that are only precise. One 1.50, 1.49, 1.52, 1.48. All of these measurements are around each other. They're very precise, but they're not accurate because the actual value is 1 kilogram, and that's not what we're coming up with. So accuracy is about how close you get to the true value. Precision is about how repeatable the measurements are. If your little brother is playing a trick on you and goes and adjusts the bathroom scale so that it always reads 10 pounds heavier, then every time you get on it, you're going to get the same measurement. It's just going to be 10 pounds more than you weigh. So that measurement is precise because you're going to get the same measurement every time, but it's not going to be accurate because it's 10 pounds off. Does that help give you the distinction between accuracy and precision? So again, no, precision is not close to the right answer. Accuracy is not further from the right answer. it's two different concepts about a measurement. It's about accuracy is how close to the right value. Precision doesn't care about the right value. Precision does not understand right. Precision does not understand the right value at all. It's about how often, to use your words, how often you get a particular value. So it doesn't matter for precision whether or not it's the actual value. All it matters is how often you get the same measurement. These measurements are all wrong. All of them are wrong, but they're all precise in the sense that they're very close together. So they have precision, but they do not have accuracy. So what I want to do, and right now I'm going to just do one last little bit before we take off, is then introduce this concept of how, so the question is, which is right? Either. So it's not that one is right and the other isn't right. It's that in a scientific measurement, you want both. You want them both to be accurate and precise. But what we're talking about right now is significant figures, and significant figures, they only talk about precision. We know that there's accuracy somewhere involved, but at the end of the day, only precision is talked about with significant figures. And so if I were to take those measurements of that cube that we know was 1 kilogram, here are some measurements. I'm going to make them all accurate. All of these are all accurate. They're all very close to the true value, right? They're all 1 kilogram, but they are increasing in precision. And we're going to start here on a week from now to talk about significant figures a little bit more. But each of these values increases in precision. What do you notice? What do you notice about each of these values? What's the sort of what do you see? What's happening as the values increase in precision? Well, Gabriel says they get smaller. Here, let me do another one. 0.000000002. That's right. They have more, and Angela's saying more decimals, and all I need you to see is that there's more digits, right? They're longer. There's just more digits, right? If the actual it could definitely not involve decimal places, right? It could be 1 million or 1 billion. We'll talk about these numbers in next time. They're all similar to 1 kilogram, so that means they're all accurate. The precision is really about the number of digits that you can get in a measurement. Let me close with this example. Let's take that bathroom scale as an example. Let's say that this bathroom scale, you get on it, and this is what it does. It'll read 10 pounds, it reads 100 pounds, or it reads 200 pounds, but it reads no numbers in between. What if you actually weigh 145 pounds? If you actually weigh 145 pounds and the only two numbers that it'll display are 100 or 200, then it'll display 100. And that's not very precise. It's not accurate either, but it's not precise. But what if I take that and instead of, so because it's not precise, I'm limiting these digits to being 0 only. But what if I expand it out and I let these be any number? So now that can be 145. What if I take the scale and not only does it say 145, but it says 145.738 pounds. The more, so generally, the more digits, boy, I don't even know how to spell digits. Somebody spell digits for me in chat. Thank you. Yeah. The more digits a measurement has, the more precise it is. And that's where I want to leave it there for now. So I'm going to stop the recording.